Right. All right. All right. So, greeting scholars. Let's see. As far as announcements go, so we just had what exam one that was due last night around midnight, like 11:59 p.m. I want to say with all of our assignments on Pearson, we get unlimited attempts, and there's only a 10% late penalty, right? So if you made less than a 90, you're welcome to like retake it and improve your score. The system is only going to show your highest score. If you are going back to do old assignments to improve your grades, like I would encourage you to prioritize your exams, as that's where you're going to get the most bang for your buck because they have the heaviest weights. Going back to do your homework is good practice, but then that's going to be a lot of work for little points, right? So I just want you to kind of be aware of that. Also, when it comes to the My Math Lab access, I know they were working out a deal to like get a reduced price. So it's still not resolved. I spoke with my supervisor earlier, and he was saying that. So it should be the case that you should be able to continue to do the temporary trial until the matter is resolved. So then I was like, well, does that mean that if the matter is not resolved by the end of the semester, will the students be able to get access to My Math Lab for free for the semester? And I think his response was, the students should be able to get temporary access for the entire semester until the matter is resolved, as far as the reduced price, right? So that's where it was this morning. So if your trial runs out the same way you started the second trial, you should be able to start a third trial and keep going until the matter is resolved. If the matter is not resolved by the end of the semester, then that might be what the case, right? Okay, so I think those are the pertinent pieces of information. Let me check Zoom one more time. That looks good, and then let's see the chat. Yeah, so okay. Let me see. So I got an email from Dr. Lamar that says I need to attend that lab. I've been attending your Zoom since the start of the year. Does that mean I've been joining the wrong class? Because when I clicked to the Zoom link they provided me, it would never open. Yeah, so it is two different things, right? So what we do together is like 90% of your class. The lab that's orchestrated by Dr. Lamar, that's a separate thing. So you have to follow her instructions. So the best thing is just to, if it's something with the lab, just talk with Dr. Lamar, just kind of communicate with her, kind of explain yourself, and then just follow her instructions. And then basically whatever she says you need to do, that's a separate portion, right? So what we do together is like 90% of your grade, 10% of your grade comes from her, right? So you have to communicate with her, reach out to her, and then follow her instructions. And so she's like, you need to pick a time to schedule or whatever she says, that's what you need to do for the lab. The lab is something separate from me. Give me just a moment. Let's see. Let's go like this. I know this is about to. Oh my goodness. Oh my goodness. This thing is just like getting worse and worse and worse. We just sorry guys, I'm coming. But yeah, so again, the lab is something that's separate. You just have to contact her and follow her instructions. I was running a little late. I was trying to make a sandwich, but it was taking way longer than I anticipated. So at least wanted to dress it before it gets like super cold, because I don't really intend to reheat this. What is that? Let's take that off. I don't even know what that is. Okay. So yeah, you just have to work that out with her. I want to say, I don't really know what it's like to be her student. So again, you just have to kind of work it out with her. But I'm pretty sure she can come up with something that'll get you back on track. You have to forgive me. Okay. Okay. So we just had exam 1 due last night, which is over sections 1.1, 1.2, and 1.3. So then today we're going to continue with section 1.4, a library of functions. Right? So this is just the next installment. And so what this is, a library of functions, we're going to start to explore how to graph these functions, right? So far in our exploration of graphing, I know we've talked about plotting points, where we choose several values of x, find the corresponding y, and plot the ordered pairs. Sometimes you'll see me use like my graphing utility, my graphing calculator to look at the shape of a function. I've also encouraged you all to like explore using desmos.com or gealgebra.com. Those are free online graphing utilities. And so those are some of the ways that we've explored graphing. So this presentation is our introduction into like graphing. And so we start with a collection of basic functions. All right, so some objectives here. 1, we like to define what do we mean by linear functions. 2, discuss important properties of functions. 3, graph square root and cube root functions. 4, we like to evaluate and graph piecewise functions. 5, we like to graph basic functions. And 6, we like to find the average rate of change of a function, right? So this is a long section. We don't have enough time to get through the whole thing together. So far, like with my students earlier, we've been making it to about slide 20. And so what that means is that on Wednesday, we'll have an option. We can either continue the presentation of this, or, which is my vote, is to go through as many homework questions together as we can. Everybody's still responsible for their own assignments or whatever, but you know, we can work on some of those questions together. And keep in mind, anything that I'm gonna say in this presentation, as far as the lecture, is already available. Is already available in my pre-recorded lecture. All right. So I took time to like go through each slide in detail. So that allows me to, that frees up time when we're meeting together. Okay. So we're going to introduce the collection of functions with the first functions, which are a couple of different linear functions. So first we have let m and b be real numbers. The function f of x equals mx plus b is called a linear function. If the slope is 0, that's similar to the y equals mx plus b like we've kind of discussed before. If m equals 0, then the function f of x equals b is called a constant function. That's going to be like your y equals some number. So it's going to be a flat horizontal line through y equals that number. If the slope is 1 and the y-intercept is 0, the resulting function f of x equals x is called the identity function. So that's going to be a straight diagonal line with a slope of 1 passing through the origin. So when we look at the graph of f of x equals mx plus b, f of x equals mx plus b is the same as y equals mx plus b, where we're using the f of x and the y interchangeably. Sometimes I'll say f of x, sometimes I'll say y. So the graph of a linear function is a non-vertical line with slope m and y-intercept b. All right. So in this image on the left, we have a positive slope. Notice as we trace the graph from the left to the right, the graph rises or goes up. Okay, so that's an example of something that has a positive slope. And then with the second one, as we trace the graph from the left to the right, notice the image falls. That has a negative slope, right? So when we're talking about positive slope versus negative slope, that's all based on as we trace the graph from the left to the right. How is our y value behaving as we move from the left to the right? Okay. So then this image on the left, we have as a constant function, right? So this is basically like you have the y equals some number. It's a flat horizontal line through whatever that number is. That slope is 0, and it's a flat horizontal line through y equals whatever that number is. That's a constant function. And then on the right, we have the identity function, which is y equals x. The slope is 1, the y-intercept is 0, diagonal line with the slope of 1 passing through the origin. Again, this is our constant function. This is our identity function. So these are the first two basic functions that we have. So here we're asked to write a linear function g for which g of 1 is 4 and g of -3 is -2. So they're asking us to fit this data to model a linear function, right? So the first thing I like to do is, this is basically saying when x is 1, the corresponding y is 4. When x is -3, the corresponding y is -2. All right, so let's write that out. So here, so when x is 1, the corresponding y is 4. When x is -3, the corresponding y is -2. Okay. So then here, what I like to do is, whenever I'm given an ordered pair like this, I like to just label it. X1, Y1. Let's clean it up a bit, make that look more like an X. X1, Y1, X2, Y2. And then they asked us to write a linear function. So I think before we made a statement saying, you know, whenever we're working with lines, it's a good idea to have 3 equations ready to go. So when we're working with lines, the first one is, I like to have the slope formula ready. So that's our rise over our run, which is our change in y over change in x. So that's going to be y2 minus y1 over x2 minus x1. Okay. So I'm going to delete that. Okay. Then I tend to like to use the slope intercept form, which is the y equals mx plus b. And then an additional equation that you can also use is the point slope form. Y minus y1 equals m times x minus x1. Okay, I'm just going to rearrange these. Use them as a reference. So I'll put them here as lines. We got our slope formula. Y equals x plus b. And point slope. Okay. Again, working with lines, we got that ready to go. And I'm just going to separate those like that. So since we have 2 points, let's start off with our slope formula. So that's going to be what? Our y2 minus our y1 over our x2 minus our x1. Again, this was our slope formula. All right, so notice the first thing I did was replace each component with a blank set of parentheses. And then we do our corresponding points into the blank parentheses. Our y2 is what? -2. Y1 is 4. X2 is -3. X1 is 1. And the blank parentheses help us to keep track of our signs so we're less likely to make mistakes. So then this is going to be -6 divided by -4, which is a positive 3/2. Okay, so that's our slope. I'm going to continue working over here. So we could use point slope. We have a point and we have a slope, and that's fine. I just prefer to use the slope-intercept formula. So my y equals mx plus b. So let's plug in the different parts that we have. Now our slope is 3/2. Now our x, I'm just going to choose the first point because it looks like it's easier to work with. We don't have those negatives, so it seems like it's easier. My x is going to be a 1. We don't know our y-intercept, and our corresponding y is 4. Okay. So then ultimately we get b equals, what, 4 minus 3/2? 8 minus 3 is what, 5/2? So we found our slope, we found our y-intercept. So then if we plug it into the linear function, our f of x is going to be equal to our m times our x plus our b. Okay. And then it is a good idea to check this. So I think I got in a space. We'll say check. Right. So we're saying, for instance, when x is 1, so if we evaluate f of 1, we're going to get 3/2 times 1 plus 5/2. That's going to be what? 8/2, which is 4. Right. So that one checks out. And then if we evaluate f of -3, let's try to clean it up a little bit. Okay. We're going to have 3/2 times a -3 plus 5/2. That's going to become -9/2 plus 5/2, which is -4/2, and that's -2. Right. So we confirm that both of these ordered pairs lie on this line. You know, that's the necessary work. Let me check on Zoom. I think there's like at least one student I'm looking for. Okay, I don't see him. Let me see. That's okay. Yes. So yeah, when it comes to the lab, you have to. I'm sure she has an office number, maybe some office hours. Like her information is there on Blackboard. So you have to reach out to her and connect with her, and then try to just explain yourself and try to work something out to get caught up. Because I think it's possible and it's feasible. But again, the lab is run by Dr. Lamar, my colleague. Ooh, I feel so much better. I didn't realize I was that hungry. Like I didn't realize I was hungry. I ate that sandwich. You know, I know you guys heard me eat it. After eating, I feel like I got like a burst of energy. Like my mind is clear. I'm not feeling like I want to go to sleep. I was struggling in my last class. I was like, man, I feel bad for this. But then that's why I was like, well, let me try to eat. And I tried to finish before I met with you guys, but it was taking longer. Anywho, right? So here's a type version of what we just experienced. Also, keep in mind that anything that you see me writing in these presentations, you know, I make a copy of these available. So if you were to go on Blackboard and go to the notes section, updated daily, it'll redirect you to Box, which you should be able to access, and you'll have a copy of basically everything that we're doing. Every time we meet, all the stuff you see me writing, I make it available. Additionally, I make the writings available for my other College Algebra 1 courses as well. I got like 3 others, right? But we all talk about the same thing. So, you know. Okay, here's a type version now. In their version, they use the point slope form, right? And so you can try that as well to confirm that it works. But they got the same results. So. 2 different ways of doing the same thing. Okay. So then now we want to explore this concept. What do we mean by increasing, decreasing, and constant functions? So let f be a function and let x1 and x2 be any 2 numbers in an open interval AB contain a domain of f. The symbols a and b may represent real numbers, negative infinity, or positive infinity. Then the following is true. Okay. So we say that f is an increasing function in an open interval AB if whenever x1 is less than x2, that implies that f of x1 is also less than f of x2, right? So the way we'll see it as we kind of start working pictorially, as we trace the graph from the left to the right, our image is going to rise or go up, right? It's going to go up. So that's what we mean by an increasing function. Similarly, for decreasing, it's the same thing. The only difference is we say that f is a decreasing function on the open interval AB if whenever x1 is less than x2, that implies f of x1 is greater than f of x2, right? So pictorially, what that means is that as we trace our image from the left to the right, it goes down, it falls. The y values go down, right? So this is an example of a decreasing function. Okay. So then we say a function is constant on the open interval AB if whenever x1 is less than x2, that implies f of x1 is equal to f of x2, right? So as we trace the graph from the left to the right, it stays flat or constant on the open interval. Okay. So then in this example, it says from the graph of G, find the intervals over which G is increasing, decreasing, and constant. Okay. I'd like to do the following. Okay, so as we trace the graph from the left to right, first we see something happen, and the change happens when x is -2. So I'm going to put a bar here just to kind of divvy it up. Then we get another change. If I can get this to respond, we get another change right here. Okay. So, and what this does, as we trace the graph from the left to the right, we see that initially the graph is increasing. So as we trace the left to right, it's going up. All right. So these vertical bars break the graph up into like 3 different regions. We got this region A, we got this region B, and this region C. All right. So we say that the graph is increasing in region A. All right. So I'm going to abbreviate that as follows. I'm going to do an up arrow. We're saying that the graph is increasing. Yes. We say that the graph is increasing. That interval, so that's based on the x-axis. The far left is what? Negative infinity. Up until the x is what? -2. Whenever we're doing increasing, decreasing, or constant, okay. Let me bring the image back up. Start the broadcast. I might be short on space. Maybe I need to delete some stuff. Optimize the video. Come on. Right here. Okay. So on region A, we say that the graph is increasing. That interval is as x goes from negative infinity to -2, right? Whenever we're doing increasing, decreasing, and constant, we typically use parentheses, right? Whenever we're doing increasing, decreasing, and constant, we use parentheses. So if we focus on region B, the graph stays flat or horizontal or constant, right? So I'm going to abbreviate that as just like a horizontal line. So we're saying that the function is constant as x goes from -2 to 3. And then in region C, we say that the graph is decreasing as x goes from 3 to infinity. Infinity always gets parentheses. And again, for the discussion of increasing, decreasing, and constant, we always use parentheses. Okay. I think I just checked Zoom, so I think you guys are good. All right, let's keep moving. And then we have a type version here. It's increasing as x goes from negative infinity to -2. It's constant as x goes from -2 to 3. And it's increasing as x goes from 3 to infinity. Okay. So we did increasing, decreasing, and constant. If a is in the domain of a function f, we say that the value f of a is a relative minimum of f if there is any interval x1 to x2 containing a, such that f of a is less than or equal to all nearby y values for every x in the interval x1 to x2. Right? So the simple thing is a relative minimum is going to be basically the bottom of a valley. We usually talk about that in the pictorial representation. When we're looking at the image, the relative minimum, these two examples here are a relative minimum because they're at the bottom of the valleys. A relative or local max are going to be these two guys. These are going to be the tops of the mountains or the peaks of the hill, right? The peak of a mountain or the peak of a hill. You can kind of identify it. These, like, for instance, the relative max occurs where a graph, I mean, there's some other conditions, but it's essentially where the graph goes from increasing to decreasing. That means we have a relative max, or where the graph, and a relative min generally occurs where the graph goes from decreasing to increasing. There's a few other conditions we need to talk about to use that. Like, we have to make sure that it's continuous and a smooth curve. Well, it just mainly that it's continuous, but that's another discussion for another time. For our purposes, the relative max occurs at the top of the mountain, the peaks of the mountain. The relative min occurs at the bottom of the valley. Okay, let's see. All right. So far we've kind of explored, what do we mean by when a function is increasing, decreasing, or constant? We've also explored relative max and relative min. So now we're going to get into this concept of what do we mean by a function being even, odd, or neither? Right? What do we mean by a function being even, odd, or neither? So we say a function f is called an even function if for each x in the domain of f, negative x is also in the domain of f, and f of negative x equals f of x. The graph of an even function is symmetric with respect to the y-axis, right? So even functions, the official definition of an even function is, whenever we evaluate f of negative x, we get back to the original. And then once we identify a function as being even, that's the same as y-axis symmetry, right? So that means if you look at the image, the y-axis will cut it in half, and the left half of the image is going to match the right half across the y-axis. If you were to fold across the y-axis, the two halves are going to match up. Okay. If we have y-axis symmetry, another way to kind of visualize it, whenever we have x comma y, we also have negative x comma y. So like whenever we get a point on the right, we also automatically get a point on the left. So if we can identify a function as being even, which means we have y-axis symmetry, we can use that symmetry to generate additional points to get our graph, right? So this is actually a discussion around symmetry. Okay. So then if we could talk about a function being even, we can also talk about a function being odd. We say a function f is an odd function if for each x in the domain of f, negative x is also in the domain of f, and then we have f of negative x equals a negative times the original. Okay. So an odd function, when we evaluate f of negative x, we get a negative times the original. For an even function, when we evaluate f of negative x, we get back to the original. Okay. The graph of an odd function is symmetric with respect to the origin, right? So if we were looking at an odd function, if you were to cut the image along the x-axis, put your thumb on the origin, and rotate the top half 180 degrees, it's going to match the bottom half. So origin symmetry or an odd function, I kind of describe that as rotational. Even function, which is y-axis symmetry, you could fold it along the y-axis and those two halves are going to match. Okay. So in this example, we're asked to determine whether each function is even, odd, or neither. So what we do is we replace each x with negative x, we simplify and interpret the results. Let me say that one more time. To do a test for even, odd, or neither, we replace each x with negative x, we simplify, and then we interpret the results. Okay. All right, so let's see it in action. So then with part A, we have g of x equals this. We want to do a test for symmetry. So first we're going to replace each x with negative x. So even before that, I'm going to replace each x with a blank set of parentheses. Okay. And then into the blank parentheses, I'm going to insert my negative x. Negative x. Negative x, right? So then if we simplify, now in that first term, we have three negatives being multiplied. We got negative x times negative x times negative x. If we have an odd number of negatives, the result is going to be negative. That second term, we have a negative 4 times a negative x. So double negative is positive. So that's going to be 4x. Is this the original? No. So then let's try factoring out a negative 1. If we factor out a negative 1 from all terms, we're going to get x cubed minus 4x. Is this negative times the original? Yes. All right. This is a negative times the original. So we started with g of negative x. We finished with negative times g of x. That's the official definition of a function being odd. Okay. So let's work on part B. So first we're going to replace each x with a blank set of parentheses, x squared plus 5. And we're going to replace each x with negative x. Okay. So negative x squared, we have an even number of negatives, so that result becomes positive. Is this the original? Yes. So we started with f of negative x, we finished with f of x. That's the definition of a function being even. Okay, let me create some space for myself. I'm gonna just rearrange this stuff and then I'll expand it a little bit later. So we'll come right back to this in just a moment. Let's work on C. So then again, we're replacing each x with a blank parenthesis. So we have h of x equals 2x cubed plus x squared, okay? And we're replacing each x with negative x. Okay? So then if we simplify, this first term, notice we have an odd number of negatives, so that guy's going to remain negative. The second term, we have an even number of negatives, so that becomes positive. Is this the original? No. If we factor out a negative, we can't get back to the original either. So this is an example of something that is neither even nor odd. Okay. Let me just rearrange the size of all this stuff. That looks decent then. It's actually over here. I think that's about the largest I can make all this. Okay. Okay. So if we were to look at the graph of part A, let's actually pull up that graph so we can look at it. So I'm going to use my virtual graphing calculator if I can get it to behave. Come on. Maybe if I unplug this, it does tantrums when that's plugged in. Sugar. Then what I would like to do, come on, this one. There you go. What am I? Y equals, yeah, I think we already got it typed in. Right, the first one, x cubed. Oh, I guess we could put the third one in there as well. X cubed minus 4x, x squared plus 5, and then the third one, 2x cubed plus x squared. 2x to the power of 3 plus x squared. Okay, I'm going to suppress this third one for right now. So now the first one we said is odd, which is an example of origin symmetry. So if we look at the graph, so origin symmetry, another way to kind of visualize it, whenever we have x comma y, we also have negative x comma negative y. So we have all these points that are symmetric and equidistant about the origin. Also, if you were to take this image, cut it along the x-axis, and rotate it by 180 degrees, the top half is going to match the bottom half. Okay, so this is, you know, this is an example of something that has origin symmetry. For even means that it's going to have y-axis symmetry, right? So that's the second one. So let me suppress the first one and engage the second one. All right. And so notice you have y-axis symmetry. If we were to take this image and fold it in half along the y-axis, they match up. And then the third one, when we look at the graph, has no symmetry, right? It's not gonna, it's neither even nor odd, right? So let's suppress the second one. Open this up. So it's no symmetry. Oh, that's misleading. It looks like origin symmetry, but it's not. Like, if you were to actually like zoom in and like do the calculations, they don't actually match up, right? It looks close, but it's not actually there. So, but that is good that we see that, because if we relied solely on the image, we might be led astray. That's why it's important to know how to do these operations without the calculator, and you can use the calculator to confirm or deny what you worked out by hand. If we just try to use the image on part C, we might think that it's odd, but then when you actually do the test, it doesn't work out. Okay, so this is as far as we made it with my students earlier. Okay, so with that, I'm going to stop the session here. Did you all have any questions for me? Are there any burning questions? Going once, going twice. Okay. Let me make a copy of this available for you all. This is the fall of 23. This is traditional College Algebra 1. The notes updated daily. And so you should be able to see my notes from my other sessions and you all. All right, so I'm going to send it here. When this bar finishes loading, you'll receive a copy of anything that you saw me writing today. The main thing is, okay, so we made it through about slide 20. That's where all my classes stop for the day. So on Wednesday, we will have an option. We can either continue working through this presentation together, or you can watch this, you know, right now, because this recording is already available. The remaining stuff is already there in my pre-recorded lectures. You can actually watch those, and in that way, on Wednesday, we can go through as much of the homework together as we can. All right. So more than likely, I'll just be working on the homework. Yeah. All right. So again, if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Take care. Peace.